Hi, this is second half of lecture 15. In this half, what we will do is we will go over some sample problems that involve conservation of momentum and conservation of energy. I will start with 15.1. This is on slide number 7. In 15.1, we have a wooden block suspended from two ropes. This block has mass m, and we have a bullet with a known mass and known velocity moving towards this block. So at some point, this bullet will get stuck in the block, and both the bullet and the block will start swinging up. They will swing up, reach some maximum height, and actually, let me draw it differently. Yeah, they will reach some maximum height, and then they will swing back. The question is, find this maximum height that the block will swing up. So to solve this problem, what I will do is I will divide it into two stages. Stage 1 is when bullet collides with the box and gets stuck in the box. So when this happens, some part of bullet's momentum will be transferred to the block's momentum, and the block will acquire some velocity v. And then there is stage 2. At stage 2, we have this block and the bullet that's stuck in the block. And this block, because it has velocity, it will start moving upwards, and it will reach its maximum elevation. Separating this process into two stages will be helpful. We will first look at stage 1, which is the collision between the bullet and the block. And during this collision, there are lots of things that are happening here, lots of interactions. Some amount of energy is bound to get lost to friction and deformation. But since there are no external forces affecting this collision, the momentum is still conserved. I will write down my conservation of momentum. I will say momentum initial is equal to the momentum final, where initial is before the collision, final is after the collision. My initial momentum is just the momentum of this bullet, because only the bullet is moving in the beginning. So it is equal to the mass of the bullet times velocity of the bullet. My final momentum is the momentum that this wooden box has, and that this embedded bullet has. They're both moving together. They have mass of mb plus m, and they have some velocity v that I don't know. Let's look at what's known and what's unknown. I know all the masses. I know initial velocity of my bullet. And this equation is easy to solve for the velocity. Velocity is equal to mass of the bullet divided by the total mass of the bullet and the block times VB. This equation makes sense. This tells me that if bullet has higher velocity, the block will have high velocity. It also tells me that if the block is heavy, it will have lower velocity after the collision. And that all makes sense. Now I will move to stage 2. In stage 2, this wooden box is swinging up. It's swinging up and it's slowing down. And it's slowing down because it's affected by gravity. We know that gravity is a conservative force, unlike friction. And since gravity is the only relevant force, we can write down conservation of energy. We can write down that energy in the beginning was equal to energy towards the end. Here, by beginning, I mean, this point in time when the box was at the very bottom and when it just got hit by the bullet and started moving. And by the final, I mean this position when this block reaches its highest point. In the beginning, okay, so I also have to choose my reference point, my 0 point, my 0 level. I will choose this to be my 0 level. Now, in the beginning, the block was at the 0 level, so it has no potential energy, but it has some velocity. So it has some kinetic energy, and the energy of this block plus the bullet is mb plus m times v squared divided by 2. At the final point over here, since this is the highest point, the block is momentarily stationary. It's not moving at that point in time. It only has potential energy, and the potential energy is mass times g times h. If you look at this equation, you will see that mass cancels out from both sides, and I can solve it for h. H is equal to v squared divided by twice g. I know the value of g. I know velocity because I just found it in my stage 1. So I can rewrite this as h is equal to 1 divided by 2g mb squared divided by mb plus m capital squared times vb squared. Let's look at this equation and let's see if it makes sense. So when I look at this equation, I see that if I have high velocity of the bullet, I will go higher, which makes sense. If gravity is stronger, then because of this g, the block will not go as high. And if the mass of the block is large, then again, since this is divided by mass, the block will not go as high, all of which kind of makes sense. Now let's move to 15.2. This is slide number 8. In 15.2, you have two boxes. This is box A. This is box B. And both of the boxes are moving with some velocities. Box B is moving with 2.5 meters per second. And box A is moving with 5.5 meters per second. The mass of block A is 1.6 kilos. The mass of block B is 2.4 kilos. You see that block A is moving faster, so eventually it will catch up with block B. They will collide, and then something will happen. We are told that block B, after collision, moves with 4.9 meters per second. So this velocity is higher than the velocity before, which kind of makes sense. If something hits you from behind, then you will start moving faster. And then there is this block A, and we don't really know what's the velocity of block A after this collision. So this velocity will be less than 5.5 because it experiences force from B, which is in the opposite direction, but we don't know whether it's less but still going to the right, or whether this reverses completely the direction, and whether the block A now moves backwards. So that's what we don't know. And the question is, how much energy was lost in this collision? So first of all, let's write down conservation of momentum for this collision. Even though energy wasn't conserved, the momentum was, because there were no external forces. My momentum initial should be equal to my momentum final. Before the collision, my momentum was 1.6 times 5.5 plus 2.4 times 2.5. This is mv. Momentum is mv. And after the collision, my momentum is 1.6 times v. I don't really know what this v is, plus 2.4 times 4.9. The only unknown in this equation is v. I will solve for v. My v is 1.6 times 5.5 plus 2.4 times 2.5 minus 2.4 times 4.9 divided by 1.6. So let's put this into a calculator. (1.6) times 5.5, 2.4 times 2.5, 2.4 times 4.9. And I'm getting 1.9 meters per second. Okay, so the velocity is indeed less than it used to be, which makes sense. The velocity is 1.9 meters per second, but it looks like the velocity is still towards the right. If the velocity reversed, I would get a negative sign here. I don't have a negative sign, which tells me that block A continues moving to the right. So now that I know my velocity, I'm ready to compute energies. I want to compute energy in the beginning and energy towards the end. Just to remind you, energy is mv squared over 2. So in the beginning, my energy was, what was my energy? 1.6 times 5.5 squared divided by 2 plus 2.4 times 2.5 squared divided by 2. And towards the end, after the collision, we have 1.6 times 1.9 squared divided by 2 plus 2.4 times 4.9 squared divided by 2. This is energy initial. This is energy final. I don't want to compute these numbers. I will leave it up to you to do that. So what you can do is you can put this into your calculators. You will get some number here, and you will see how much energy was lost. So in general, when you have collisions, in the ideal case, your energy is conserved, but very often some energies will be lost to sound and internal friction and deformation. So in general, you should expect your final energy to be less than your initial energy. So compute these numbers and see by how much the energy changed. Now let's move to problem 15.3. This is slide number 9. In 15.3, we have 3 boxes. Box 1 box 2, and box 3, they have decreasing masses. Box number 1 is 1 kilo, box number 2 is half a kilo, and box number 3 is 1/4 of a kilo. And the first box is moving with the velocity of 4 meters per second. Box number 2 and box number 3 are initially stationary. They tell you that no energy is lost in these collisions, and they ask you to compute velocity of box number 3 after all the collisions have taken place. I think this problem is kind of similar to one of the problems that you have in homework, except in homework, you start with a smaller box and you move on to a more massive box. Let's think about what will happen here. This box 1 will obviously move towards box 2, and at some point, the box 1 and the box 2 will collide. Because of this collision, box 2 will now start moving, and eventually it will collide with box number 3. And because of that collision, box 3 will start moving with some velocity. That's the velocity that we have to find. For simplicity, let's split this into 2 parts. Part 1, collision 1, is when 1 collides with 2, and part 2, or collision 2, is when 2 collides with 3. For collision number 1, they tell me energy is conserved, and I know that momentum is conserved because there are no external forces. So I can write down both the momentum conservation and the energy conservation. My momentum conservation is momentum in the beginning is equal to momentum at the end. And my energy conservation is that energy in the beginning is equal to energy towards the end. Let's start with the momentum. What's my momentum in the beginning? In the beginning, only box 1 is moving. So the momentum is 1 times 4. After this collision, now both box 1 and box 2 are moving with some velocities that I don't know. So I will write 1 times V1 that I don't know, plus 0.5 times V2 is my momentum, and that must be equal to 4. Let's see how this works for energy. In the beginning, only box 1 was moving, so I have 1 times 4 squared divided by 2. And since no energy was lost, they tell me this must have been distributed to the final energy, which is 1 times V1 squared divided by 2, plus 0.5 times V2 squared divided by 2. So I have 2 equations, and I have 2 unknowns, V1 and V2. From now on, this is algebra. The way I will solve it, I mean, there are many ways of solving this. So what I will do is I will do the following. First of all, I will cancel out these 2's because they're kind of annoying, and all terms have this 1/2, so I can cancel them. And now what I will do is I will take my first equation and I will solve it for V1. So from this equation, V1 is equal to 4 minus 0.5 times V2. What I will do now is I will take this V1, and I will substitute it into my second equation in here. Let me rewrite that equation. I have 16 equal to 4 minus 0.5 V2 squared plus 0.5 V2 squared. I will simplify this. I will open the brackets. I get 16 minus 4 v2 plus 0.25 v2 squared plus 0.5 v2 squared. 16 and 16 will go away, and I will have 0 is equal to negative 4 v2 plus 0.75 v2 squared. I can cancel one set of v2s, and then I can solve this equation for v2. From here, I will get v2 is equal to 4 divided by 0.75. Four divided by 0.75. My calculator tells me that's 5.33. So I get 5.33 meters per second. This kind of makes sense. My first box was moving with 4 meters per second. It collided with the second box, which was lighter. So I expect the second box to be moving faster. 5.33. Now that I know velocity of box 2, I can move to collision number 2. For collision number 2, I will basically do almost the same thing. I will write that my momentum is conserved. And I will write that my energy is conserved. For the momentum, I will write that in the beginning, I only had box 2 moving. So that's 0.5 times V2, which is 5.33. And towards the end, I had both box 2 and box 3 moving. So for box 2, I will write its velocity as V2 prime. And for the box 3, I will write 0.25 times V3. Similarly, I can write equation for energy conservation. In the beginning, I only had energy in box number 2. That's 0.5 times 5.33 squared over 2. And then I have this energy redistributed into 0.5 times V2 prime squared over 2 plus 0.25 times V3 squared divided by 2. From now on, I can solve this exactly in the same way as I solved collision number 1. I'm not going to do that here to save time, but if you do exactly the same thing, you will get V3. And I suspect that this V3 will be even higher because you have even smaller object. So the number that you get will probably be larger than 5.33. So complete this at home and see what you get. Now let's move to problem number 4, 15.4. This problem is from your textbook. And this problem is different from the ones before because now we have a 2-dimensional collision. You have two objects, object A and object B. They are moving. Object A is moving like this. Object B is moving like that. They collide with each other. Something happens here. We don't know what happens exactly. And after this collision, object A is moving this way. And object B is, actually, we don't know what happens to object B. So I will draw an arrow. This is velocity of A before collision. This is velocity of B before collision. This is velocity of A after collision. And this is velocity of B after collision. And the velocity of B is unknown. They tell you that VA is 15I plus 30J. Velocity of B is negative 10I plus 5J, and VA prime is negative 5I plus 20J. Just to remind you, I and J mean that, this is the X component, this is the Y component, yeah? Whatever stands in front of I is the X component, whatever stands in front of J is the Y component. I cannot say that the energy was conserved, but I can say that the momentum was conserved because there were no external forces. So I will write down the momentum in the beginning is equal to the momentum at the end. Momentum in the beginning is m VA plus m VB. Momentum at the end is m VA prime plus m VB prime. I'm using the same letter m here because both objects A and B have the same mass, which is 2 kilos. And if you look at this equation, you will see that because of that, mass actually cancels out. So we are left with VA plus VB is equal to VA prime plus VB prime. This equation is a vector equation. However, we have to write down this equation in X and in Y separately. Let's start from X. The X component of VA is 15. So I have 15 plus negative 10 is equal to negative 5 plus whatever is the X component of B prime. So the X component of B prime. For the Y, I have 30 plus 5 is equal to 20 plus whatever the Y component of VB prime is. Both of these equations turned out to be pretty simple to solve. For VB X component, I will have 15 minus 10 plus 5. That's 10 meters per second. And for VB prime Y, I will have 30 plus 5 minus 20, that's 15 meters per second. Now that I know the B velocity, I can compute the energy. Just to remind you, energy is mv squared over 2. Energy is a single number. So if your velocity has components x and y, what you do is you just add the x component squared and the y component squared. Let's do that. Let's compute energy initial first. In the beginning, I had both object A and object B moving, and their energies were mv squared over 2. So my total energy is 2 kilograms times 15 squared plus 30 squared divided by 2 plus 2 kilograms times 10 squared plus 5 squared divided by 2. So this is my initial energy. And now I will compute my final energy. My final energy is 2 kilograms times 5 squared plus 20 squared divided by 2 plus 2 kilograms times what's the velocity of B after the collision? Okay, it's here. Plus, so 10 squared plus 15 squared divided by 2. This is my energy in the beginning. This is my energy at the end, after the collision. I'm not gonna compute these numbers. I will leave this up to you. So compute these numbers. You will get some number here for the initial energy. You will get some number here for the final energy. And you will see whether or not the energy changed. And if it changed, whether it went up or whether it decreased. You could, if the energies are equal, it means that there was no energy loss or gain. If your energy went down, it means that there were some friction forces or deformation forces that took away energy. And if the energy went up, it means that when those two objects collided, there was some sort of energy release. So maybe this collision triggered some sort of explosion. But anyway, compute those numbers and check it out. So that's all I had for you today. There is also part 1 on Canvas. We will have a Zoom meeting on Friday from 12:30 to 2:30. If any of this is unclear, if you have extra questions, please join the Zoom room and we can discuss all of this plus homework on Friday between 12:30 and 2:30. Thank you very much.